Welcome back. In this video, we'll introduce some tools and functions for working with continuous probability distributions. We'll start by defining a probability density function. So what can we use to help us describe how much probability is within a particular area? We'll talk about how to find continuous probabilities. We'll also define a new type of function for us called a cumulative distribution function. So let's start with the probability density function, or the PDF. So we say that a continuous random variable y is a random variable that takes values over a continuous set. So that means that within some interval or some range, any value is possible. There are infinite possibilities for a continuous random variable. So we say that y is a continuous random variable, then little f of y is a probability density function, or a PDF, if the following are true. So first, f of y must be non-negative. It must be greater than or equal to 0 for the entire range of y. The second restriction, or the second condition, is that the integral of the PDF over its entire range must be 1. Now in practice, we usually don't integrate this PDF from negative infinity to positive infinity. We just integrate everywhere that the PDF is non-zero, and we call that region the support of y. Third condition, for some set S within the real line, the probability that y is in S can be found by taking the integral over S of the PDF. So in other words, in order to find probability in a continuous space, we integrate. Now let's say that we want to find the probability that A is less than Y, which is less than B. We find that by taking the integral starting at A up to B of the PDF with respect to Y. Now, with any continuous random variable, there's a fun little property that comes from this. The probability that y takes on a single individual value is equal to 1. Now, there are a few ways, it's not equal to 1, it is equal to 0. There are a few ways to justify this. Probably the simplest way conceptually is this. With a continuous random variable, we are assuming that any of an infinite number of values within a range is possible. So the probability of any of an infinite set is then 0, 1 over the number of possibilities. Another way to think about this is using that area under the curve definition. If we take the integral from A to A, we're left with just the area of a straight line, which is 0. So let's take a PDF, say c times y squared, for some random variable y that's defined from -1 to 2. And let's figure out what value of c we actually need in order for this to be a valid PDF. In order for this to be a valid PDF, we want to integrate over the entire range where y is non-zero, or over the entire support, and get back 1. So we'll take the integral from -1 to +2. We'll set that equal to 1. This gives me that c over 3 times y cubed, evaluated from -1 to 2, must be equal to 1. Solving for that, we get that 1 is equal to 3c. So then c is equal to 1/3. Using this c, we want to find the probability that y is greater than 1. So the probability that y is greater than 1 can be found by taking the integral from 1 to 2, 2 being the upper bound because that is the upper range of support for y, of 1/3 times y squared with respect to y. We get 1/9 times y cubed, evaluated from 1 to 2, which is 7/9. So looking at a plot of this PDF, the area under the curve from 1 to 2 represents 7/9 of the total area. There is some probability associated in this -1 to 1 range, but relative to the 1 to 2, those outcomes are much more likely, have more probability associated with them. So there are some key differences between PDFs, which we'll use for continuous random variables, and PMFs, which we'll use for discrete random variables. both of them give us ways to measure or describe the probability within a particular reason. So that's a really great similarity between the two. The major difference is that while the PMF, the probability mass function, gives you the exact probability of an outcome, the probability density function, the PDF, does not. Instead, what the PDF measures is the density. So think of it like a relative chunk of the probability in some range. Let's take a look at another example. So suppose that the random time t of a radioactive particle that's been emitted is proportional to a decaying exponential function of the form e raised to the negative lambda t. So since we're looking at our random variable t being a time random variable, it makes sense to restrict it to positive time points. Let's find the PDF of t. So we'll take our PDF, we'll integrate it over the entire range of support, so from 0 to infinity, and figure out what value of c makes this equal to 1. Working with the exponential function, our integral should be negative 1 over lambda times e raised to the negative lambda t. We'll evaluate that from 0 to infinity. Plugging in 0 to infinity, we get that 1 is equal to c over lambda. So then the constant c that makes this a valid PDF is lambda. This turns out to be a fairly important probability function. This is an example of the exponential function. We'll come back to it quite a bit in the semester. So let's let y be a random variable. We then say that the cumulative distribution function, or the CDF of y, is capital F of y, which is the probability of y up to a particular point. Probability that y is less than or equal to little y. For continuous y, we find that cumulative distribution function, or that cumulative CDF, by integrating from negative infinity up to y. So let's find the CDF of our exponential distribution. We have the PDF here, plugging in lambda for our constant c. We can find the CDF by integrating up to some arbitrary value. So I'll find this by integrating up to arbitrary t. It may help some people to change the variable of integration. Strictly speaking, that's not really necessary, and that's not something that I tend to do, but it's something that you can totally do at home if that helps keep things straight. So f of t, our cumulative distribution function, or our CDF, is negative e raised to the negative lambda t, evaluated from 0 to t. And we will end up getting this. So the CDF for the exponential distribution is capital F of t equal to 1 minus e raised to the negative lambda t. So let's take a look at an example of another cumulative distribution function. So this cumulative distribution function is a bit more complicated than some of the others. We get 2y times e to the negative y squared, where y is greater than 0. Our PDF looks a little like this. Let's find the CDF. Now, for those of you watching at home, this would be a really great point in the course to dig out some of those Calc 2 notes and review your rules of integration. I will go ahead and post some of the rules of integration as a reminder online, just as a reference point for you guys to use. So in order to find the CDF, capital F of y, we'll integrate from 0 to y, our PDF, 2y times e to the negative y squared with respect to y. Using u substitution, we end up with the following result. The CDF is equal to e raised to the negative y squared power, evaluated from 0 to y. Capital F of y then becomes 1 minus e to the negative y squared. Let's take a look at these functions side by side. So we have our PDF in blue on the left, our CDF in green on the right. So as we are moving up, as we're increasing y, we start to accumulate probability very quickly, especially around where y is equal to 1. Then we begin accumulating that probability a bit more slowly. Once y is equal to 2, we've covered most of the probability. We've gotten about all of the area under the curve. Our CDF then levels out. The CDF will always be a non-decreasing function. So strictly speaking, we are accumulating probability as we go. The CDF then will also be bounded. The lower limit will be 0, the upper limit will be 1. The PDF itself has no such bound. The PDF must be non-negative, but there is no upper limit on the bound. So let's find a way to express the probability that y is between a and b in terms of the CDF. So the CDF gives us the following. We know the probability that y is less than or equal to a is the CDF evaluated at a. We know that the probability that y is less than or equal to b is the CDF evaluated at b. Assuming then that a is less than or equal to b, the CDF of A must be less than or equal to the CDF of B. So then to find this probability, if we know what the CDF is, then we can just take the CDF of B minus the CDF of A. So let Y have the PDF below. We want to find this probability. We want to find the probability that Y is between 1/2 and 1.5. So here we have a PDF that is split, that has several cases to it. So because this PDF is a piecewise function, it turns out that the CDF, or the cumulative distribution, will itself be a piecewise function too. So for 0 less than y less than or equal to 1, we'll find the PDF in that range. So capital F of y is the integral from 0 to y of 2/5 times dy. Or the CDF is 2/5 times y. For the next piece of this function, 1 less than or equal to y less than 2, our CDF is the cumulative probability that has occurred up to 1, so 2/5 times y, plus the integral from 1 to y of 2y over 5 dy. So then our CDF, once you evaluate that integral, is 2/5 plus 1/5 times the quantity y squared minus 1. So using the CDF, and here we have simplified things just a little bit with that 1 to 2 piece, we can find the probability that 0.5 is less than y is less than 1.5 by taking the CDF evaluated at 1.5 minus the CDF evaluated at 0.5. So we get 1/5 times 1.5 squared plus 1/5 minus 2/5 times 0.5. So our CDF tells us that the probability within that range is 0.45. Again, here is what these functions look like side by side. So we have the PDF in blue on the left, the CDF in green on the right. The piecewiseness of this function then is represented by the fact that we have a sort of jagged edge with this PDF. The CDF shows that same sort of jagged edgedness, but it's not as pronounced. So let's end this video with some properties of a cumulative distribution function, and we'll talk about these properties a bit more during our time together in class. So a function, capital F, is a cumulative distribution function if it satisfies the following properties. So the left-hand limit, the limit as y approaches negative infinity of the CDF is 0. As we move toward the right, we begin accumulating probability. So then the probability, the limit as y approaches positive infinity of the CDF must be 1. For any x less than or equal to y, the CDF of x must be less than or equal to the CDF of y. And then finally, for all real a, the limit as y approaches a to the right of the CDF of y must be equal to the CDF of a. In other words, CDFs are right continuous functions. They may not necessarily be left continuous functions. You'll see that behavior in the discrete case. We'll end this video here. In the next video, we'll talk about how to find expected value and variance for continuous random variables. See you then.